Hello friends, I welcome you in lecture number 19 on graph theory. In previous lecture we have defined cut vertex of a graph, and in this lecture we are going to discuss one question on cut vertex which was asked in GTU Winter 2022 exam. First we recall the definition of cut vertex. Suppose we have some connected graph, say G, then a vertex V of this connected graph G is called a cut vertex if the subgraph G minus V is disconnected. If after removing vertex V and all edges incident with vertex V, whatever subgraph we obtain is disconnected, then vertex V is called cut vertex. So here we are given one graph and we have to list out all the cut vertices of the graph. And first you have to define cut vertex. So cut vertex is the vertex of a graph such that after removing that vertex and all edges incident with that vertex, we obtain more connected components as compared to the given graph. Now here you can see that this graph is obviously a connected graph. So we will check for each and every vertices that whether after removing that particular vertex, whatever subgraph we obtain is disconnected or not. Here given graph is connected. So if after removing some vertex, say vertex A, we obtain disconnected graph, then vertex A is called cut vertex. Otherwise vertex A is not a cut vertex. So first I will remove vertex A and then I will see whatever subgraph I obtain is connected or disconnected, and there is only one edge incident with vertex A. So I remove that edge and vertex A. So we can see after removing vertex A, we obtain this subgraph, and this subgraph is clearly a connected subgraph. So here I have written that removing vertex A and all edges incident with A, we obtain this subgraph which is connected, and therefore A is not a cut vertex. A was a cut vertex if the graph obtained from G after removing vertex A and all edges incident with A was disconnected. But here we obtain connected subgraph, therefore vertex A is not a cut vertex. Similarly we check for vertex B. So for that I have to remove edges containing B as endpoint. So there are 1, 2, 3 and 4 edges. So I am removing these edges whose endpoint is B. This is the edge whose endpoint is B. This is also an edge with B as endpoint. This edge is also, and this one is also, and we have to remove vertex B also. So now you can see whatever graph we obtain after removing vertex B and all edges incident with vertex B, we obtain this subgraph, and this subgraph is clearly disconnected. There are two components. One component is component having only one vertex or isolated vertex A, and another component is this one. So because we obtain a disconnected subgraph, B is a cut vertex. So in that way you have to check for each and every vertex. Here I have drawn the original graph for every vertex, and I am showing you how I am removing that vertex and all edges incident with that vertex. Now we check for vertex C. So we remove edges whose endpoint is vertex C. So this is one edge, this is another edge, this is another edge, and we have to remove vertex C also. So after removing vertex C and all edges incident with vertex C, we obtain a subgraph which is not disconnected, or we obtain a connected subgraph, therefore vertex C is not a cut vertex. Now we check for vertex B. So for that I am removing this edge also I have to remove, and I have to remove this edge also, and finally I have to remove vertex B also. So we can see we obtain disconnected graph, or whatever subgraph we obtain is disconnected with two connected components. This is one connected component, this is another connected components. Therefore vertex D is a cut vertex. Then we check for vertex E. So let's remove this edge. This is the edge whose end point is E. This is another edge, this is also, and this is also, and we have to remove vertex E also. So we obtain disconnected subgraph, therefore vertex E is a cut vertex. Then we have to check for vertex F. So let's remove this edge, this edge, this edge, and vertex F, and we obtain connected subgraph. So F is not a cut vertex, because after removing vertex F and all edges incident with vertex F, we obtain a connected subgraph. So F is not a cut vertex, E is a cut vertex, D is a cut vertex, and B is a cut vertex. So list of cut vertices is we have to list out all those vertices. A is not a cut vertex, B is a cut vertex, then D is a cut vertex, and E is a cut vertex. So B, D and capital E are cut vertices. This is the answer to the given question. Let me again check. B, D and E. E is a cut vertex, D is a cut vertex, C is not a cut vertex, B is a cut vertex, and A is not a cut vertex. So this is very easy question. You just have to remember the definition of cut vertex. And if your graph is connected, then cut vertex means after removing that vertex and all edges containing that vertex, we obtain disconnected subgraph. And keep in mind that if our graph is not connected, or if we have a disconnected graph, then it will have some connected components. If our graph is disconnected, then it will always have at least two connected components. So suppose G is a disconnected graph, therefore there will be some connected components in graph G. Suppose there are n connected components in a disconnected graph G. Now suppose after removing vertex V and all edges incident with V, whatever subgraph we obtain, if that subgraph has more than n connected components, then vertex V is called a cut vertex. In the case of disconnected graph, suppose disconnected graph has n connected components, and after removal of some vertex V and all edges incident with V, we obtain more than n connected components, then V is called a cut vertex. And for connected graph, it is very easy, because connected graph has only one connected component, graph itself. So if after removing vertex V, that graph produces a disconnected subgraph, then we can say that V is a cut vertex. So this was about this question asked in GTU Winter 2022 exam, and we stop here. I hope you like this lecture. Thanks for watching.